So we're going to cover population dynamics very quickly. A lot of you probably know about population dynamics. So this deals with ecology, the study of the earth and organisms and how those things interact. So where we are. I just said ecology is the study of organism interactions with each other in the environment. These processes occur at multiple levels. When we did organismal physiology, we talked about the organism. It goes organism to population to community, ecosystem, biome, and eventually the biosphere or planet Earth. So each level of organization emerges from the processes of the level below it. And so we're going to look at population, which is all members of a species in a contiguous area. And so these populations and their interactions are dynamic. So there's theory and reality for how populations grow. In theory, there's two ways. Organisms enter a population via birth or immigration with an I. They exit via emigration with an E or death. And it's really simple. If your birth rate and your I migration are greater than your death rate, what happens to your population? It increases. If the inverse happens, if your death rate is higher than your birth rate, what happens to your population? It decreases. And if they're equal to each other, no growth. Okay? So that's kind of the theory. Model 1 is about exponential growth, or what we call the J curve of population growth. And basically, it says that the growth continues indefinitely and it assumes that there's no resource limitation. It assumes there's enough food for everybody. There's enough water for everybody. There's enough shelter for everybody. There's not rampant disease that's killing off large portions of the population. So it can be defined as N over T, or the change in the number of individuals over time. And you can see on the formula on the left, the J-curve graph, the blue one, it says R max N. R is the per capita rate of increase, or what we can call how many offspring per individual in the population. If you want your population to grow, and you have two individuals, and they are going to mate, how many children must they have in order for the population to grow? 3 or more. If they have 2, it's what's called replacement. Because mom and dad are going to die eventually, and those 2 kids take their place. If mom and dad only have 1 kid, and everybody in the population only had 1 kid, what happens to population size over time? It goes down. Okay? As long as R is positive, population grows. If R is 0, population is stable. And if R is negative, population declines. Model 2 is what's called logistic growth, or S-curve. And it decreases in an S-curve. It might start off kind of looking logistic, but eventually it starts to decrease and turns towards an S-curve because the population reaches what's called K, or carrying capacity. Carrying capacity is just the maximum number of individuals that the environment can support for that population. Okay? And so it basically says there are limitations in resources that cause a population to reach its carrying capacity. If you have a certain given area and there's only so much food and only so much water and only so much shelter, then eventually if you go above carrying capacity, what's going to happen to the population? There's going to be competition for those resources. And the best fit survive to reproduce, and the least fit die. It's natural selection. Okay? So reality. Populations are structured differently. So it becomes extremely difficult to actually get a relative accurate measure for a population size. So there's one method that's common among biologists called mark recapture. You go out, you mark a lot of individuals of the same population, you track them over time, and then you go out and you recapture them, and you see, did the population size grow? Did the population size decrease? And then that gives you a relative birth rate and death rate, and you can also see relative immigration rates And so you can make an extrapolation for how big the population size is based off of a small subset of the population. Is it completely accurate? No. And in fact, even measuring human population size, they say our world is about 7.4 billion people. That's just their best guess based off of what countries report for birth rates and death rates and immigration rates, etc. So it's just a scientist's best guess as to how big a population is. And that's because populations are distributed basically in three different ways. They can be clumped together, they can be kind of a uniform distribution, or they can be random. And so you can see these starfish in this picture are clumped together. You can see that the penguins here kind of have a uniform distribution. And you can see these wildflowers in this field are just random. If you can, I don't know if you can see it, but they kind of stretch all the way towards the back of the picture. And so it's just a random distribution. They're not all over the land. There's clumps, or there's areas where there's green grass and not wildflower. This is all measured through demographics. How many people are there? What's their birth rate? What's their death rate? How long do they live? How often do they reproduce? How much do they survive? What type of survival do they have? So how do real populations grow? Essentially, both ways. Typically, exponential growth is only seen in a small population. Like here you have an example of some elephants, like conservation measures in the early 1900s. Elephant population was really low. Conservation measures were implemented, and survival rates increased, and the elephants began reproducing exponentially. So the population grew exponentially, particularly around 1960 to 1968 or so. Typically happens, again, only in small populations, well below carrying capacity. Logistic growth is much more common, and so typically there's an oscillation around K, or carrying capacity. Now, can a population go above carrying capacity? Yes, it can. But once it goes above carrying capacity, there's competition for resources. So what happens to the population once it goes above carrying capacity? It goes down to carrying capacity or below it. So you get that oscillation around the ideal population size. Okay? You can see that in this graph as well. And you can also see that, never mind, I thought there was one more. So evolution affects these history traits. Okay, so a life history trait is kind of a trait that affects the life table, how long that organism is going to survive, what things are going to cause that organism to not survive. And so there's a cost and a benefit to all adaptations. Evolution is not purposeful. It does not evolve just solely ideal traits. There's good traits, there's bad traits. The best survive to reproduce, but there's also mutations and whatnot. So it's not always going to be beneficial. We're going to skip that. We're going to skip that. We're going to skip this. Now, the environment affects population growth. And the effect of population density on population growth is measured in these graphs. Q is equilibrium. B is density dependent birth rate. I'll get into density dependent in a minute. And M is density independent or death rate. So if B is greater than M, the population grows until equilibrium or Q. If M is greater than B, the population shrinks. We kind of already said that at the beginning. We can definitely see that in this example. We have the snowshoe hare and a lynx. Now, what do you notice, particularly around right here? When the snowshoe hare population increased, what happened to the lynx population? It increased. Why would the lynx population increase if the snowshoe hare population increased? More resources for the lynx to eat. So, conversely, what happened to the lynx population? It wasn't exactly even. If you look at the graph and you kind of come down from the peak, the lynx population actually grew probably the year after the snowshoe population was really high, because the lynx that lived during that year where there were a lot of snowshoe hares had plentiful food, so less energy went into hunting and more energy went into reproducing. But conversely, if the snowshoe hare population declined, the lynx population declined because there's less food for all of that population. Okay? So density-dependent population regulation. These are factors that impact a population's ability to grow. Things like competition. There's only so many resources. Predation. Waste accumulation. Territoriality. I always want to put an extra T in there and say territoriality. And intrinsic factors. Now, also disease. If you get a large population into a small confined area, it's very easy to pass disease. So, how does human population growth impact our planet, and what does human population growth look like? First off, our growth as a species is the underlying root of all anthropogenic ecological problems. What do we think this word anthropogenic means? Human caused. It's the underlying root. Our growth is the underlying cause of all of the ecological problems that we know about. All of the plastics in the oceans, excess carbon dioxide in the atmosphere, even, let's just say, like Chernobyl. You guys know what Chernobyl is? Yeah, the nuclear reactor in the 1980s in the Ukraine. So our factors are all of this. So historically, human population around the Industrial Revolution took off exponential growth. And so if we look at the graph, I'll go back here. If we look at the graph, there was actually a small dip in human population during the Middle Ages because of the plague. Industrial Revolution happens, invention of modern medicine happens, people start living longer, people start having more babies, human population growth explodes. It took about all of history to 1960 for the world to reach 3 billion people, and in the 56 years since, we've added 4.5 billion more people. So it's exponential growth. Growth rate slowing, but it's still increasing. And so this is kind of this graph represents the human population growth. By the time you guys are around 50 to 55 years old, and I'm in my mid-60s, it's projected that human population growth will only be about 0.5% a year. Now, at current rates, that would mean that we're still adding 40 million people to the world every year. So what's the world's carrying capacity? When are we going to run out of resources? When are we going to run out of food and water? And what's that? We already are?
No, I said 11 hours.
Oh. So it's a big debate. We don't know. That video doesn't work anymore. So this is on your review. An age structure pyramid. You can look at an age structure pyramid and determine how a population is growing. If you have a really, really wide base of the age structure pyramid, it means your population is young. And what is that young population going to do around 15 to 20 years old? Start reproducing. And so then that pyramid stays wide. But if you look in the middle, Italy, there's no growth. They have a greater concentration of people in their 30s and early 40s. They've probably already reproduced. And so their population is going to get older as time goes on. And they're probably birth rate equals death rate. And then United States, we have a much more distributed age structure pyramid, so we have pretty slow growth. Okay? And like I said, we don't know what carrying capacity is going to be. Some people say we've already passed it. Other people say maybe 8 billion, 10 billion, 12 billion people. I don't know. Okay? We'll find out.
Catch us on the next episode.
Okay, so that